Welcome back to the channel. Here in this video I will be solving the last year physics exam. It's year 2022 physics exam for grade 12 advanced. So I will be going through the 25 questions, and also please don't forget to join the Telegram and the WhatsApp group in the description below. So in this video I will be covering chapter 5, 6, 7 and 8. And here we go with our first question. So the figure shows the magnetic field lines of a permanent magnet, as you see here. Which of the following is correct when determining the north pole and south pole of the magnet? So as we know, always north pole and south pole, that these are the two ends of a magnet. The field lines always start from the north and are received by the south pole. So of course, as you see in the picture, I'm not sure if it's clear, but you can guess, you can see that the field lines start from B and enters A. So of course B is the north pole and A is the south pole. So always the field lines start from north and end or terminates on the south pole. So this is you can find that on chapter 7.1. So we continue with the next question. What is the constant mu zero called? So what do we mean by that? Also, you can refer back to chapter 8.1, where you can see that the magnetic permeability of free space, which is mu zero, which is the constant, and it's equal to 4 pi by 10 to the power of minus 7. Here we are with question 3. It's regarding chapter 6.4. So which of the following circuits will function properly? So you should know one main idea here, that a voltmeter always supposed to be wired in parallel. However, an ammeter is wired in series. So let's talk about these four circuits. Here, what's the mistake in this circuit? Where ammeter here, you can see it's wired in parallel. So of course this is wrong. What about that one? Here also you can see the same mistake. Ammeter never wired in parallel. What about that one? We have two mistakes. Voltmeter is in series. That's wrong. And here ammeter is wired in parallel. That's wrong. So that's the correct circuit, where both voltmeters are branched in parallel and ammeter is wired in series. So this is the correct answer. Next question, also regarding section 6.1. So according to the figure here, this one, we have I1, which is 0.5 ampere, I2 0.2 ampere, and asking for the magnitude of I3. So according to Kirchhoff, if you remember the Kirchhoff junction rule. So what this rule stating that the sum of the current and at a junction must be equal to 0. So let's count them. I1 is entering the junction, so it's plus I1. What about I2 and I3? I2 and I3, as you see, they are leaving the junction. So we're supposed to put minus for them. So minus I2 minus I3, all of them are equal to 0. So here they are asking for I3. So we arrange the equation. So I3 will be equal to 0.5, which is the I1, minus 0.2, which is I2. So the answer is 0.3 ampere for I3. Question number 5. For the electric circuit shown in the figure, if the battery's electromotive force is 12 volt, the resistance is R, which is 2.4 ohm. So what's the electric current? So this is a simple application of Ohm's law. So here Ohm's law, where I is equal voltage over the resistance. So voltage is of course 12 over 2.4, and the answer is 5 ampere. Next question, also regarding Ohm's law. According to the figure here, this one, when a third resistor is added in series to the two resistors connected in series. So here we are adding one more resistance to the circuit. So what do you think will happen to the electric current I. So what do you think? So this is according to Ohm's law, as I told you, I is equal voltage over resistance. So we are adding the resistance. And as you see, resistance and I are inversely proportional. They call it علاقة طردية. Okay, so if R increase, I decrease. So R and I are inversely proportional. So if we increase R, so what will happen to the current I? It of course will decrease. Question number 7. 3 identical resistors connected together in parallel this time. They are connected in parallel. So if equivalent of the 3 resistors is 6 ohm. So the total of them, all of them, are equal to 6 ohm. So what is the resistance of each resistor? So let's apply the circuit. So that's the circuit, 3 resistors, 3 identical resistors in parallel. So let's apply the inverse relationship where 1 over R total is equal to 1 over R plus 1 over R plus 1 over R, because they are similar to each other. So you do the same denominator, so you get this equation. 1 over R total is equal to 3 over R. So what's the unknown here? R. This is the unknown. So you arrange the equations. So R is equal 3 times the total resistance. So it's 18 ohm. Next, with question 8. So the figure shows 3 identical resistors connected in circuit. The switch S is initially closed, as you see here. If safe, open the switch. So what happened to the currents flowing through RC? So here we have RA, B, and C. Now the switch is closed. So if we open the switch, what will happen to the current flowing through RC? It will increase, decrease, or stay the same? We'll see. So here's Ohm's law again, where I is equal voltage over the resistance. And here also they are asking for the current. So they are asking for I. So remember, here RC is parallel to the battery. So that's the voltage across RC. Also it's 12 volt, whether the switch is open or closed. So V is constant in that case. It's always 12 volt for RC. Okay, so as you see from the equation here, I depends on the voltage and the resistance. As I told you, the voltage V is constant because they are in parallel. So it's 12 volt across the battery and 12 volt across this resistance. What about R? Also R did not change. So neither V nor R changed. So of course I will not change. So I will stay the same. We continue to question 9. For the circuit shown in the figure, if another resistor with equal resistance was connected with R in parallel. So here another resistance connected in parallel, as you see here. So what happens to the magnitude of the current flowing through the battery? So here's the extra resistance, which is switched in parallel. And of course asking for Ohm's law because they mentioned the current. So what will happen to the current? So again we need to calculate R total. How to calculate R total? By applying the inverse relationship. 1 over R total will be equal 1 over R plus 1 over R, because they are identical resistors. So R total will be equal R over 2. So the total resistance now is divided by 2. So you can tell what will happen to the current. If R decrease, as we discussed earlier on, I of course will increase. So if R is divided by 2, I will be doubled. I will be multiplied by 2, because they are I and R are inversely proportional. So I will become twice. It will be multiplied by 2, and that's the reason. Yes. From chapter 7.3, here is the question. In the equation B stands for the magnetic field, equal mv. M stands for the mass of the particle multiplied by its velocity over qx. So what does x represent? So what's missing in this equation? So from chapter 7.3 you can tell that r, which is the radius of the path taken by the charge in a magnetic field, is the missing. So we miss r in that equation. So which is r equal mv over qb. So if you arrange the equation, b will be equal to mv over qr. So it's the radius. With next question from chapter 6.2, asking, according to the figure, if the reading of the sensitive ammeter A is 0. So talking about Wheatstone bridge, if you remember. So this circuit is called Wheatstone bridge. So if R1 is equal 6 ohm, R2 here 4 ohm, R3 8 ohm. So what does R4 equal to? So we need to calculate the value of R4. So from that chapter you can find this equation. So R4 will be equal R1, which is the other side of the resistance, multiplied by R3 over R2. When you apply the equation, when you apply the numbers, the value of R4 will be equal to 12 ohm. Continue with chapter 5.4. A rechargeable battery is rated at 3 milliampere per hour. So what is this total charge in coulombs units? So we need to convert. So this question is only about conversion of units from milliampere per hour to coulomb. So what this amount is equal to in coulomb. So simple equation here. You can find it in chapter 5.4. 1 milliampere per hour is equal to 3.6 coulomb. So to convert from milliampere to coulomb, you should multiply by 3.6. By the way, I promise you next time to make my handwriting better. So you need to multiply 3 milliampere per hour, 3, and then you multiply it by 3.6, and the answer is 10.8 coulombs. What about the next question from chapter 7.2? So which of the following is equal to the unit of the magnetic field strength Tesla? So Tesla is equal also to what? With what unit? It's Newton per meter over A. It's NS over CM. Is it NA over M or NM over CS? So what do you think? Yes, from that equation you can tell that F, which is the force, equal Q VB. So you arrange the equations. So now B is equal to the force over QV. So let's discuss the units of these parameters. So force, of course, in Newton. Q is in coulomb, and V, which is meter per second. So here meter over second. So we have double division. So now S turns upward. So now it's in the numerator. So it's NS over CM, which is equivalent to this option, NS over CM. Continue with the same chapter, chapter 7.2. So according to the figure, in what direction the proton P will be deflected as it enters the constant magnetic field B? So here we have a proton moving inside a magnetic field. So that's the motion of the particle. As you see, P is moving that way. So that's the motion of the particle. B is inside the screen because you see X, you see the X sign. So this means that the magnetic field is to the inside of the screen. So we need to define the direction of the force. So we need to calculate the direction of the force. So what do you think the direction of the force? So we need to apply the right hand rule. Okay, so look at this. So this is the right hand rule, where V, the motion of the particle going that way, V, B is inside the screen, so F will be upward. So F is moving upward. So which one of these options is equivalent to that answer? So is it out of the page? No. Into the page? Not. Toward Y negative? No, it's upward. So it's toward the Y positive. So the force is upward. It's going up. So the force of the force applied on the charge in that magnetic field is upward. with next question, question number 15. So a particle with charge Q equal 3.2 microcoulomb and speed of V enter a magnetic field of 0.2 Tesla. So what's the magnitude of the magnetic force on the particle? So we need to calculate the force. So I'll remind you of this equation from chapter 7 where F equal QV multiplied by B. So remember, this is a scalar product. Sorry, it's a vector product. This equation is in 3 dimensions. So we need to multiply it by sine the angle. Why here I consider the angle as 90? Because as you see from the picture, V, the velocity of the particle, is to the left and B is downward. So what's the angle between them? Yes, it's a right angle. So the angle is 90. And sine 90 is 1. So how to calculate the force? It's simply QVB. So Q is given 3.2 by 10 to the power of minus 6 because it's mu coulomb, multiplied by 520 meters per second, multiplied by B, the magnetic field, which is 0.2. So you do the calculation and the answer is 332.8 micronewton. Question 16. According to the figure, on an isolated segment of wire of length L carries a current of magnitude I and an angle of 60 degrees. So with respect to the constant magnetic field, which is 5.4 by 10 to the power of minus 2 Tesla. So what's the magnitude of the force on the wire? So here talking about the current and the magnetic field. So you can go back to chapter 8.2 to check the equation. And this is the given. L, the length of the wire, the current, the angle, and the magnetic field B. So asking for the force. So what equation combines all of that? Yes, it's where F is equal IL multiplied by B. All of them are in, of course, vector product. So F will be equal IL multiplied by B multiplied by sine the angle, as we discussed in the previous question. So I, which is 1.5, length is 8.3, B is 5.4 by 10 to the power of minus 2, and the angle is 60. So you apply the numbers and the answer is 0.58 Newton. We continue the next question. An electric device with a power of 968 watt is connected to a source of electric force where V is equal to 120 volt. So what's the resistance? So you have the power and the voltage and asking for the resistance. So what do you think the equation is? Yes, so it's power equal V square over R. So asking for R, you need to arrange the equation. So R will be equal V square over P, and the answer is 50 ohm. With the next question, this is question number 18. So a cylindrical aluminum wire is 32 meters long and has a resistance of 0.2 ohm. If the resistivity of the aluminum is 2.8 by 10 to the power of minus 8 ohm per meter. So what's the radius of the wire? So asking for R, and we know the resistivity and the resistance of the wire and its length. So the hint here, the area of a circle is pi r square. So you need to use this equation where R is equal rho L over the area. And area, as they mentioned, it's equal to pi r square. So you need to put 2 in 1. You need to replace equation 2 in equation so 1. So R will be equal rho L over, instead of area, now it's pi r square. So you arrange the equation where R is equal square root of rho L over RP. So this is the square root of that amount, and R will be equal to 1.198 by 10 to the power of minus 3 meter. With the next question, so which of the following is equal to the unit of Siemens S? So we have 4 options. So you need to remember that S, which is the Siemens, is the unit of the conductance G. So S is the unit of the conductance. And as you remember also, the conductance is 1 over, it's the inverse of the resistance. If the resistance is, according to Ohm's law, is U over I, U stands for the voltage and I stands for ampere. So J, which is the conductance, which is S, the unit of the conductance, will be the inverse of that amount. So it will be A over V. It will be the inverse, 1 over R. So it's A over V. So where is A over V? It's here. So that's the correct answer. So 1S is equal or stands for ampere per volt. Excellent work. So we are approaching the end of the video, and here we are with question 20. So if the equation between charge and time is given by Q equal 5t squared plus 3t. So what's the correct expression of the current I? So from chapter 5.1, we have that relationship where I, the current, is equal dq over dt. So you have here to derivate the function, because the current I is the derivative of the charge. So that's the derivative. I is equal to dq over dt. You need to derivate that function, 5t squared plus 3t. As you remember, the derivative, we need always to minus 1 for the power. So the power, which is here 2, supposed to be minus 1. And the power also should be multiplied by the coefficient, if you remember. We studied this in term 1. And here 3t, it will be transformed to 3. So that's the derivative where I is equal 10t. Why it's 10? Because 2 multiplied by 5 is 10 and the power is minus 1. So 2 minus 1 is 1. So here there is power 1, but we don't put it. Plus 3. Okay, so that's equivalent to that option. We continue the same chapter, section 2. So which of the following is not true? This means that all of them are true except of one. For current density J and the current I. So let's go back to this section and you can find out this relationship where J, the current density, is equal to I, which is the current over the area. And also we find out this where I, the current, is equal to the integral of J multiplied by dA. So let's go through all these options. So all of them are true. So yes, this is equivalent where I equal integral of GdA. So this is equivalent to this one. So this is true. But because here they are searching for not true answer. So this is also true, equivalent to the first option where J is equal I over A. And this one also is true because they are stating that the unit of the current density equal to ampere per meter square. So because ampere stands for I and meter square stands for A. So it's I over A, which is correct also. So the only option available, or the last option, is the unit of current density ampere per meter. So it's ampere per meter, the current density is ampere per meter, which is wrong. It's supposed to be meter square. So this is not true, the option that they are searching for. Next question from chapter 7.5. So a coil X consists of 400 loop and a coil Y consists of 900 loop. So we have two coils. If the torque on each loop of the coil X is equal to the torque on each loop of coil Y, so they have the same torque. Okay, so what's the ratio of the torque? So we need to do the ratio as they said. So it's tau X over tau Y. So tau X, which is the for coil X, which is 400, and coil Y, which is 900. So it's 400 over 900, which is 4 over 9. Question number 23. An RC circuit consisting of 12-volt battery. The charge on the capacitor as a function of time is given by this equation. So that's the equation, which is 6 multiplied by 10 to the power of minus 4. All of them are multiplied by 1 minus exponential of t over 0.1. And from that section, we can find out this equation of charging a capacitor, which is Q equals CV, which is 1 minus exponential minus T over RC. So that's the equation given by them. So they ask what's the capacitance C of the capacitor. So they ask for this one. So this is the unknown C. So how to find out C? So by comparison. So by comparing these two equations, you can see they are too similar to each other. So CV is equal to 6 by 10 to the power of minus 4. And this is the exponential part, also is equal to each other. So, but we are focusing on that part because it contains C, the unknown. So CV is equal to 6 by 10 to the power of 4. How to calculate C? So C will be equal to 6 by 10 to the power of minus 4 over the voltage. Here the voltage is given, it's 12 volt. So C will be equal 6 by 10 to the power of 4 minus 4, over 12. And the capacitance will be equal to 5 by 10 to the power of minus 5 farad. Question number 24 from Kirchhoff's rule. This is so interesting. So when analyzing loops in electric circuits, which of the following assumptions is correct for the conventions? So to solve this question, so these are the 4 tables, and we need to find which one of them is the wrong one. Sorry, all of them are wrong, but we need to define which one is the correct one. How to know? We need to refer back to chapter 6.1, Kirchhoff rule, and that's the conventions. That's the guide. Every time you are confused, you need to refer back to the guide in Kirchhoff rule. So remember the direction of the loop and the direction of the current. So that's how we need to define or give you the answer for this question. So if the direction of the analysis means the direction of the loop, okay, so if the direction of the loop is the same as the direction of the current, you need to put minus IR. So if the direction of the loop is opposite to the current, you put plus IR. If the direction of the loop is the same as the voltage or going from the positive side, so it's positive VMF. If it's opposite to the battery or leaving from the negative side of the battery, so you need to add minus VMF. So let's discuss these tables. I'm not sure if it's clear, but you can tell, we can spot some wrong answers here. So if the same as, so the direction of the analysis of the direction of the loop is the same as the voltage, it's supposed to be positive. Here I don't know, I'm not sure if you can notice the minus. So this is a wrong table. So this table is wrong because it's not compatible with that one. That's the correct table. So it's not compatible to this one. So let's go to the second table. Here also is another mistake. Direction of the analysis or direction of the loop. If it's the same as the battery, so it's supposed to be positive. So this is the same mistake repeated in both tables. Let's go. What about this one? What is the mistake in this table? If the direction of the loop is opposite to the current, it's supposed to be positive, because look here, where if the direction of analysis is opposite to the current, it's supposed to be plus IR, but here they put minus, so this is wrong. So the only table available or left with is the first one here. So all of them are compatible with this one. Yeah, here we are with the last question with Kirchhoff rule also. So what's the current flowing through the loop shown in the picture here? So here we have a simple circuit. We have 2 batteries and 2 resistance. So, and asking for the direction and the value of the current. Okay, so is it clockwise, counterclockwise? Is it 1 ampere, 2 ampere? So I'll give you a hint here. So let's consider that's the direction of the current going that way. It's counterclockwise. I consider the current going as a counterclockwise. What do you mean by counterclockwise? It's opposite the direction of motion of the watch. So this is clockwise, if you notice, and this is the counterclockwise going that way. So I take the current as the direction of the current as counterclockwise. What about the loop, the direction of analysis? I decided to take the loop that way. That's the direction of analysis. I need to analyze the circuit going that way. Here you are free, you can take the other way, that's no problem. Okay, also for the current you can take the other way, there is no problem. But I decide to solve this question to take these ways. That's the direction of the loop going clockwise. So direction of the current is counterclockwise, but the direction of the loop is the direction of the current is counterclockwise and direction of the loop is clockwise. So let's solve this. Let's turn this circuit to an equation. So it's plus 3 minus 6 plus 1i plus 2i equals 0. Why it's plus 3? So let's start discussing this. So this is the loop going that way, and this is the battery. So the loop is leaving the battery from the positive side. So it's plus 3. Here also the loop continue to the other battery. Here the loop is leaving from the negative side. So it's minus 6. Here the loop continue. The loop is going that way and the current is going the other way. So both are opposite. So you need to add plus. So if you are confused with the sign, you need to refer back to the table. So here it's plus 1ii. We continue. The loop will continue this way. Also here another it's opposite also to the direction of the current, so it's positive 2, which is the resistance, multiplied by the current 2i. So the only unknown here in this equation is I. So 3i is equal to 3, so the current is equal to 1. So that's it for this exam. Thank you for your attention. Thank you for watching this video, and please don't forget to join the groups in the description below.